First of a short series of 2 videos on the fundamentals of polymerization and polymers. Polymers are essentially large molecules, macromolecules, a molecule made by joining small molecules together in a repeating chain. Those monomers could either be the same or they could alternate between 2 different monomers, AB, AB, AB. Polymers form in 3 basic ways. You can have a free radical polymerization, condensation, or ionic polymerization. For the remainder of this video, we will look at those 3 in some detail. Starting with free radical mechanisms. These are called addition polymerizations. You start off with a species called an initiator. That initiator essentially is split into 2 radicals, a radical being a molecule with a lone single unpaired electron, through various initiation processes. Once those radicals are free in a system, they will react with monomers. Since the radical has an odd number of electrons to begin with, the combination of the radical and the monomer will still have an odd number of electrons and form another radical. This leads to the chain propagation step, which will continually go on as more and more monomer is added. The chain is finally terminated when 2 different radicals join together. The kinetics of this is straightforward based on radical chemistry. The concentration of free radical initiator is always going to be a constant. Therefore, you get a rate that's a composite rate constant where initiation and termination are balanced, and you see the fractional orders indicating that a free radical was present. Initiation can happen in one of 2 major ways. You can have chemical initiation by use of a catalyst. As previously mentioned, any surface or high surface area is highly reactive. When a molecule attaches to that surface, it forms a bond, bonds are weakened, and the molecule can split into 2 radicals. In this case, the rate law is relative to the concentration of catalyst is present, because the catalyst will be equal to the amount of radicals that are formed. The second type of initiation process is a photochemical initiation. In this case, you have a molecule interacting with light. That light has enough energy to split the bond between the molecules and again form 2 radicals. Now the rate is equivalent to the concentration of initiator, because once again, one initiator will form two radicals, but it's not dependent upon a catalyst or a chemical property to be initiated. The process is called photochemical equivalence, where one bond is broken by 1 photon. And you wind up with a photon yield that essentially tells you what percentage of photons have reacted. As an example, let's look at the case where a 100-watt lamp emitting light at 275 nanometers produces a quantum yield of 0.18. To find the rate of initiation, there's several steps that have to do with the units. If I have a 100-watt lamp, that means I'm emitting 100 joules per second. For a photon at 275 nanometers, that produces 7.22 times 10 to the minus 19 joules for a single photon. So at 100 joules per second, that means I have 1.4 times 10 to the 20 photons per second entering the reaction. At an 18% or 0.18 yield, 18% efficiency, that means I have 2.5 times 10 to the 19th initiations per second, or, turning into moles, 4.14 times 10 to the minus fifth moles per second is the initiation rate. The second method of polymerization is called step growth polymerization. This uses a condensation mechanism that should be familiar from organic chemistry. If I have two hydroxycarboxylic acids reacting, the carboxylic acid, by definition, donates an H+, stripping the hydroxide group, the OH-, forming water. This is an esterification reaction where the rate is first order in both reactants, assuming I have a single monomer that gives a rate equal to K times the concentration squared. One end of the molecule is always going to be an alcohol, the other end is always going to be an acid, so this will continue producing water, and you will get, after many esterifications, you will get, repeating over and over again, a polyester. The rate of this occurring, as mentioned, is simply equal to the concentration of reactant A plus reactant B, or the concentration of C squared, where if this is integrated, the original concentration minus the concentration left at given time C divided by the product of those two is equal to KT, leading to a term F, which is the fraction of the groups reacted, how many groups remain divided by the original amount. So you get a term F divided by 1 minus F is equal to the original concentration by KT. This allows you to determine the rate of a condensation mechanism because a plot of F divided by 1 minus F versus C0 times T is linear, and the slope of that will be the rate constant of the reaction. Step growth polymerization can also occur through an ionic mechanism. This comes in two flavors. In the first case, you have a cationic mechanism. In this case, a Lewis acid interacts with a solvent to form an acid complex. This is the initiation. That acid complex will react with any alkene to oxidize the double bond to a single bond and produce a carbocation. Once again, that carbocation will propagate and open up more alkene bonds, and the chain will grow. This is the chain initiation step, or the chain propagation step. Termination in this case can happen one of two ways. Either the bond can be reduced to an alkene ending the chain, or a carbocation can reduce the first carbon and also end the chain. This is two ways termination can occur. The rate of propagation is simply going to be equal to the concentration of the unreacted monomer and the carbocation chain. Once again, in polymerization, you have a steady state where initiation and termination are balanced. The rate of initiation depends upon your amount of Lewis acid, the solvent, and the monomer, while the rate of termination is equal to the carbocation chain. So you get a rate of propagation that's the same sort of composite rate constant with the K of propagation times initiation over termination times the concentration of Lewis acid times the activated solvent times the monomer squared. This squared term is unique in polymerization and is indicative of a cationic mechanism. As can be expected, in addition to a cation, you can produce an anion. In this case, an organometallic is split as an initiator. The organic anion will react with the monomer now, and that will also produce another anion, which will continue to react with further monomers, and that will produce the chain propagation. What is interesting with the anionic case is that there's actually no termination step. At no point can two activated chains join with each other, and there is nothing to oxidize the chain present in the system. This is what's known as a living polymer. It is actually the most controllable type of polymerization, allowing you to get very specific amounts of molecular weight and monomer included in each chain. You choose when to actively quench it by either adding CO2 or water into the system. That's the only thing that will stop the chain from propagating. So, you have a rate that simply is equal to the propagation, which is equal to the concentration of monomer times the anionic chain. The other thing that's unique about this is initiation is 100% efficient. So at any given point, the amount of organometallic present is equal to the sum of the activated chains. So overall, the rate of propagation is equal to a constant times the concentration of the monomer times the original concentration of the organometallic. In all three mechanisms, you can either have a single monomer or multiple monomers. Chain propagation steps allow you to structure the polymer easier in terms of the ordering of the monomers. Lastly, the length of a polymer chain is highly variable even within a given sample. Of all of the mechanisms we've seen, most of them had termination steps, which would occur at any given time, giving you a large dispersity in the size of a polymer. The length of a polymer chain is statistically found through something called the random walk. You can have multiple monomers linked together. However, since the carbon-carbon bond has a 109-degree angle, they will not form a straight line. They will essentially form a curving loop. Z is the length of this loop, the net distance traveled in the random walk equation. If I take L number of steps, meaning I add L number of monomers, and N is the number of steps taken, statistically, you wind up with the following relationship, which tells you the probability that the traveler or the walker has moved between Z and Z plus D, the change in Z, in N number of steps of length L. That's the statistics. In terms of a polymer, you now have a three-dimensional shape. So you have your 4 pi r squared. And now you're talking about r, the radius of the polymer. So the random walk probability turns into the following equation that you see before you with the exponential. From this, you can calculate the root mean squared length of the polymer. It's the integral of that function And that winds up simply being equal to NL squared. Since the bonds can form at an angle, you get an angular component to this, 1 minus cosine theta bond angle over 1 plus cosine bond angle theta. So you get what's called the root mean squared average distance that a particle can travel or a chain can grow. To demonstrate this, an example. I have a polymer of polymethylene polymer that has a mass of 100,000 grams per mole or 100,000 Daltons. I know the carbon-carbon bond distance is 155 picometers, and I know the carbon-carbon bond angle is 109.3 degrees. The number of steps I took, if I have 100,000 grams per mole, and each monomer is a CH2, 14 grams per mole, I've taken 7,143 steps. To find the root mean squared distance traveled, I simply plug those numbers in for the number of steps with the length of the step and the angle. And you find out that that polymer chain, no matter how long it might be stretched out, extends a distance of approximately 37 nanometers. I hope you found this video useful. And in the next video, we will look at how to find the weight of a given polymer, once again, given the fact that there's a large amount of dispersity in that weight. Thank you very much for listening.